Today I'm talking about application of Gauss's law. Using Gauss's law, we can find electric flux density as for various charge distribution, for example, point charge, line charge, volume charge, and surface charge, and etc. So our purpose is to find electric flux density. We can find electric flux density by using this formula. This formula include integration. So firstly, we have to choose Gauss's surface, and after we choose Gauss's surface, we eliminate this integration, and it is very easier to calculate electric flux density. So when we choose Gauss's surface, the Gauss's surface satisfies below two requirements. If the Gauss's surface satisfies two requirements, this calculation become very easier. First requirement is only normal component of electric D vector exists. The tangential component of D vector shall be zero, does not exist. For example, we have point charge Q, and we think Gauss's surface as the surface of sphere. Like this. This is Gauss's surface, and the radius is r. The surface is this. This is a surface of sphere, and constants r. This is surface. We introduce spherical coordinate. This is theta direction, and this direction is pi direction. This is r direction. So the direction of electric flux density is r direction. This is a normal component of the surface plane, and no tangential component of the electric flux density. This is the first requirement. So this D vector is only r component, and theta and pi component doesn't exist. This component is the tangential component, so tangential component of electric flux density doesn't exist, and only normal component of electric flux density exists. This is the first requirement. The second requirement is that the magnitude of electric flux density shall be constant. It means you have point charge Q and the Gaussian surface as the surface of sphere. P1, P2, P3 is on Gaussian surface. And for example, the magnitude of electric flux density at P1 is 3, and electric flux density of P2 must be 3 if the magnitude of electric flux density at P2 is 2. This is not constant, 3 and 2. It means the magnitude at the point on Gaussian surface has the same value. This is the second requirement. This is called magnitude of D vector shall be constant. So next we try to find electric flux density for point charge. So let the point charge Q Coulomb be located at the origin and Q. In this case, spherical coordinate is appropriate, and because Gauss's surface is the surface of sphere with the radius r. The point, if we deal with point charge, the Gaussian surface is the surface of sphere, and when we deal with line charge source, the Gaussian surface is the surface of cylinder. So because this is the point charge, the Gaussian surface is the sphere surface, and this is the radius is r, and surface differential area is this area. The surface area we enlarge this surface and this surface. This is theta direction, and this is pi direction, and this length is r d theta. This length is r sine theta d phi. So ds is r d theta multiply r sine theta d phi. The direction of the differential area is outward the differential area. This is the r direction, so the ds vector is r d theta multiply r sine theta d pi a r, and d vector is only r component, the normal component exists, the tangential component doesn't exist because the surface of sphere is the Gaussian sphere. So dr ar vector. So the purpose is to find electric flux density. So we find electric flux density by using this formula, vector plus ds vector. This means the sphere is enclosed by the Gaussian surface. So this is d vector is dr ar vector. Dot ds vector is this r square sine theta d theta d phi. This integration is for area integration. This integration is double integration. The range of theta is from 0 to pi, and range of pi is 0 to 2 pi. So dr is constant because the sphere surface is Gaussian surface. So this is dr, and r square is also constant, r square, and integral from 0 to 2 pi d pi multiply integral 0 to pi sine theta d theta. So this is dr r square, and this is 2 pi. This is minus cosine theta from 0 to pi. This is 2. This is 4 pi r square dr. dr is the magnitude of electric flux density. So left hand side q is q, and right hand side and 4 pi r square dr. The magnitude of electric flux density dr is q over 4 pi r square. The electric flux density is q over 4 pi r square ar vector. This is electric flux density for point charge. In summarizing, we find electric flux density by using this formula, and right hand side become this, and left hand side is q, and ds is magnitude of electric flux density, and this is 4 pi r square, and numerator is q and ar vector. This is electric flux density for point charge. How about electric flux density for line charge? As you know, line charge has only low component field. So d vector is a low vector, d pi a pi vector, and dz az vector. This is tangential component, and this field is 0 on Gaussian surface, and this is line charge, and the surface, Gaussian surface of line charge is the surface of cylinder. So this is line charge, and the height of cylinder is L, and we using this formula, and we can find electric flux density. This means the cylinder is enclosed by Gaussian surface. The surface, we have three surfaces. Its cylinder is enclosed by three surfaces. The surface is top surface, and bottom surface, and this is side surface. And this is for top surface, and d vector dot ds vector, plus bottom surface d vector dot ds vector. And for side surface, we have to calculate d vector dot dx vector. We have already known d vector is d low a low vector, and ds1, ds2, ds3. ds1 vector is ds1, and the direction of ds1 vector is outward vector is az vector. This is g direction. And the s2 vector is the s2, and the direction of the s2 is outward. It's minus az vector. The s3 vector is the s3 multiply. The direction of the s3 is low direction, because the side, the differential area of side is c and low. This is differential area of side, and perpendicular direction of this differential area is low direction. So this is a low vector. So we input this d vector, ds1 vector, ds2 vector, ds3 vector into the integral. This is right hand side d vector and ds vector. This is first right hand side. Right hand side is integral top. D vector is the d low a low vector. Dot ds1 vector is ds1 a z vector plus for bottom surface, bottom Gaussian surface, and d vector is the d low a low vector. Dot ds2 minus a z vector plus for side surface d low a low vector, the ds3 a low vector. A low vector dot az vector is 0, because a low vector and az vector is perpendicular. Similarly, a low vector dot minus az vector is 0, so this is 0 and this is 0. Only side surface integration survive, so this is integral for side surface d low ds3. So this surface is Gaussian surface. D low is constant, so d low integral side ds3. What is ds3? The differential area is this. This is the ds3 and ds3, and this length is dz, and this length is low d phi, and ds3 is dg multiply rho d phi. So this is the low, it's a double integral low d phi dz. The range of pi is from 0 to 2 pi, and the range of L is 0 to L. Low is also constant, so the low multiply 2 pi L. This is right hand side. Left hand side is Q. Left hand side is Q is line charge density. This total charge is this charge. Line charge density is multiply L. The L, and right hand side and left hand side shall be equal. So this is 2 pi low d low L equal low L multiply L. L is deleted, and this is, we can find d low. This is magnitude of electric flux density is low L over 2 pi low. So electric flux density is d low a low vector. So this can be d low is low L over 2 pi low a low vector Coulomb per meter square. This is electric flux density of line charge. How about electric field is? Electric field in free space is d vector over epsilon 0. So this is 2 pi epsilon 0 low L a low. This is same as we find in previous section. So in summarizing, in this case cylindrical coordinate, this case is the source is line charge. When source is line charge, cylindrical coordinate is appropriate, and Gaussian surface is surface of cylinder. So we Q is integral d low dot ds. If we choose Gaussian surface, the calculation is easier. It means integration is disappear, and d low 2 pi low L. So electric flux density is rho L over 2 pi rho A rho vector. Rho L is line charge density. So next is the application of line charge to find electric flux density. Consider a coaxial cable which has inner conductor radius A and outer conductor radius B, and dielectric material between inner surface and outer surface. I will draw. This is inner conductor, and this radius is A, and outer conductor is radius of outer conductor is B, and between inner conductor and outer conductor is filled with dielectric material, and this is coaxial cable. Coaxial cable and inner conductor radius A is very small. The inner conductor is this. This is L. This inner conductor and A. The A is smaller, and the more smaller, it becomes line charge. So to find electric flux density in coaxial cable field is same as finding electric flux density in line charge source. So charge density. So another information is the charge density rho S inner is on the outer surface of inner conductor. It means this is outer surface of inner conductor. This surface charge is outer conductor of inner surface. This surface, and this surface charge density is rho S inner. So this is rho S inner. So we try to find electric flux density in coaxial cable field. We're using this formula d.ds. So firstly, we left hand side is Q is rho S inner multiply the area, side area of cylinder. This yellow area is the side area of cylinder. So this is pi direction and d direction. This is differential area ds, and this enlarge this area, and this g direction and pi direction. This length is dz, and this length is rho d pi. dg multiplied rho d pi is ds. So this is integration rho S inner rho d pi dz, and this is integration for area. This integration is double integral. So at this case, rho is constant. Rho is A because the radius of inner conductor is A. So the range of pi is 0 to 2 pi, and the range of C is 0 to L. So this is rho S inner is constant. A is also constant. A rho S inner multiply 2 pi L. Second is right hand side is d vector ds, and this means the cylinder encloses the surfaces, top surface, bottom surface, and side surface. And we have already known the d vector has only rho component and line charge. This is 0 A rho, and this is, so the electric flux density is this direction, and rho direction is this direction, and ds vector is, there is rho d pi dz, because the Gaussian surface is this surface. This is rho. So in this case, this is not A, just is rho, and rho is and B. It is a different, depends on how we choose Gaussian surface. So this ds is rho d pi dz, and d vector is d rho d a rho vector. We input this into the integration, and this is double integral d rho a rho vector dot rho d pi dz a rho vector. A rho vector dot a rho vector is 1. The range of pi is from 0 to 2 pi, and the range of z is 0 to L. So this is 2 pi rho d rho L. So left hand side and right hand side must be same. So left hand side is a rho s inner. Rho s inner is surface charge density of inner conductor. The surface charge density is located on outer surface of inner conductor. So 2 pi L, and this is 2 pi L rho d rho. So d rho is magnitude of electric flux density is a rho s inner over rho. This is magnitude of electric flux density. The electric flux density is d rho a rho vector. So this is a rho s inner over rho a rho vector. The unit is Coulomb per meter square. So we found the electric flux density as summarizing. So we find electric flux density by using this formula, and this is Q inner. The Q inner is surface charge density and the area of side area of cylinders. This is rho s inner multiplied 2 pi AL, and right hand side is 2 pi ds rho L. ds is magnitude of electric flux density, and electric flux density is d rho and a rho vector. Rho is between A and B. So we try to find the total charge of the outer surface of outer conductor. It means the outer surface of outer conductor is this conductor, this surface. The charge is located on outer surface of outer conductor. Like blue sky is located on, charge is located on blue sky surface. This is rho s outer, and surface charge density of outer conductor. This is, so this, if this total charge is plus Q, and the total charge of the outer surface of outer conductor is minus Q, right? So Q inner is minus Q outer by Gauss's law. So we calculate Q inner. We have already calculated Q inner. So we repeat again. Q inner is surface charge density multiply the area, the side area of cylinder. Side area of cylinder is A d phi dz. The range of pi is 0 to 2 pi, and range of z is 0 to L. This is 2 pi L rho s inner, right? 2 pi L rho s inner A. Q outer is, this is similar to Q inner. The surface charge density outer conductor, outer surface of outer conductor multiply the side area of outer conductor. This is B d pi dz. This is B, and the range of pi is from 0 to 2 pi, and the range of z is from 0 to L. This is 2 pi L rho s outer multiply B. So Q inner is equal to minus Q outer. 2 pi L rho s inner A equal minus 2 pi L QS outer B. The QS outer, it means surface charge density of outer surface of outer conductor is minus A over B rho S inner. So we can also find the surface charge density of outer conductors like this. This is the surface charge density of outer conductor, in detail outer space of outer conductor, right? So we take an example. The first example is coaxial cable length is 50 centimeter and inner conductor radius is 1 millimeter. Outer conductor radius is 4 millimeter. So inner conductor radius is 1 millimeter. Outer conductor radius is this is 4 millimeter, and this is coaxial cable, and the length is 50 centimeter, right? Centimeter, and the space between conductor is filled with air. That this is the permittivity is epsilon 0. When total charge of inner conductor is 30 nanocoulomb, the charge of inner conductor is located on the outer surface of inner conductor, located of side surface of this cylinder. The total charge is 30 nanocoulomb, and we let the surface charge density of outer surface of inner conductor is below S inner. So find the surface charge density on each conductor, rho S inner, rho S outer, and electric field and electric field intensity. We have to find this for quantity. And first is we try to find surface charge density of inner conductor, surface charge density of outer space of inner conductor. We can use Q inner is rho S inner multiply the area of the side surface of cylinder. Side surface of cylinder is this is the radius 1 millimeter, so 10 to the power minus 9 a d phi dz. Range of pi is 0 to 2 pi and 0 to L. L is 50 centimeter. The 50 centimeter is 0.5 meter. So this is, we have already known, this 30 nanocoulomb. 30 multiply 10 to the power minus 9. So we can find the rho S inner is 9.55 microcoulomb per meter square. This is constant, so this is out of the integration, and we can calculate this. Second is rho S outer and minus A over B rho S inner. Minus A is 1 millimeter, B is 4 millimeter, and rho S is 9.55 microcoulomb per meter square. This is minus 2.3875 microcoulomb per meter square. This micro is 10 to the power minus 6. So we try to find electric flux density. We find the magnitude of electric flux density is a rho S inner over rho. We have already derived this formula and operate in coaxial cable line. This is A is 10 to the power minus 3 multiply 9.55 and micro is 10 to the power of minus 6, and low. This is 9.55 over low and nanocoulomb per meter square. And electric field can be found by using electric flux density. This is E vector is d vector over epsilon 0. So d vector is 9.55 over low a low vector nanocoulomb per meter square, because coaxial line can be considered as line charge. So this is only a low component exists. So this is low 9.55 a low and 8.845 multiply 10 to the power minus 12. This is 10 to the power minus 6. The unit is volt per meter. This is electric field. The next question is the point charge 0.225 microcoulomb is located at origin. The origin is 0.25 microcoulomb. This is charge quantity. This is not volume charge density, line charge density, and charge density. This is not charge density. This is charge, and this is millicoulomb per meter square. This is surface charge density. It's located at r equal 1 centimeter. This is rho s is 2 millicoulomb per meter square, and r is 1.8 centimeter. So we have a charge, and the charge density is minus 0.6. This is 1.8 centimeter, and this line surface charge density is minus 0.6 millicoulomb per meter square. The question is find the electric flux density at r equal 1.5 centimeter. This 1.5 centimeter, and this lead surface is Gauss surface. This is 1.5 centimeter. This is Gauss surface. We can find the electric flux density by using this formula. The d vector is just to have r component, the r vector, and the s vector is r sine theta d theta d phi, r jacob sine theta d theta d phi, and this q is charge quantity inside Gauss's surface. So the charge quantity inside Gauss's surface. So this charge is not included. So right hand side Q is 0.25 nano 10 to the power minus 6 coulomb plus this charge is the surface charge density multiplied the area, the surface area of the sphere with radius 1 centimeter. So this is r square. R is 1 centimeter square. Sine theta d theta d phi. Theta is 0 to pi and 0 to 2 pi. Rho s is 2 millicoulomb per millicoulomb is 10 to the power minus 3. This is Q. And we can find that this Q is we can find the Q. This is Q, and this is left hand side, and right hand side is integral d vector that ds vector. This is double integral dr r square sine theta d theta d phi, and range of theta is 0 to phi, and range of pi is from 0 to 2 pi, and this is 4 pi r square. R is 1.5 centimeter, so multiply 1.5 multiply 10 to the power minus 2 square ds, right? So ds is the magnitude of electric flux density is 4 pi 1.5 multiplied 10 to the minus power of minus 2 square, and numerator is q, this q, and the ds is 977, approximated 977.3 microcoulomb per meter square. So electric flux density is 977.3 A r vector microcoulomb per meter square. This is the answer for this question. So today we discuss how to find electric flux density by formula Q is integration d vector dot ds vector. When we choose Gauss's surface, this right hand side can be simplified. It means integration is disappear and magnitude of d vector is constant, so we can calculate the electric flux density easier. So thanks for listening this video, and see you next time. Bye bye.